Okay, so hello everyone. Welcome to our last seminar talk this semester. We have Matija Bucić from the University of Vienna. Matija did his PhD at ETH Zurich, then he moved for 4 years to Princeton, and very recently he moved to a permanent position at the University of Vienna. Today he will tell us about spanning tree spectrum, so we are glad to have you here.
Thank you very much for the introduction, and just that hopefully permanent position again. First of all, thank you all for coming, and big thanks for hosting me, for being such nice hosts over the past 2 days, in particular to Bartek and Marcin for being great hosts and spending so much time with me working on some cool stuff. So I want to tell you something about a problem which I find really cool and that has kind of connections to lots of different things and also a bunch of open problems still related to it. So I'm more viewing it as a kind of talk advertising some very nice open problems, and also on the way I'll tell you some nice results and some things that we know. At any point, if you have questions or you don't hear me or you don't see me, if you're on Zoom, I guess, then just stop me, and I'm happy to try to explain more or be clearer. Also, if you can't read my writing, please tell me. I'm trying to write in block capitals because my handwriting is horrible. Very good. So let me start with the definition, what I mean by this tree spectrum, and it's actually one of the kind of most basic notions and objects in graph theory that really pops up a lot. So let's give you a graph. I will denote by tau of G. The number of spanning trees of G. Right, so you take your favorite graph. So this is a graph function. You can evaluate it on any graph, and it spits out a number, a positive integer, or well, 0 if it's not connected, which just says how many spanning trees you have. And this is a function that has been studied for a very, very long time, goes back to 19th century, and probably the most famous result involving it answers the question of how large this function can be. So what is the maximum value it can take? If you think for a second, it's a monotone function, so if you keep adding edges, you just increase the number of spanning trees. So in particular, clique will maximize it. And does anyone know what this function evaluates when we count the number of spanning trees of a complete graph on n vertices? So this is called Cayley's formula, and it's something that is taught in many classes on graph theory, and it has lots of nice proofs, and the answer is n to the n minus 2. And so there is really by now kind of a variety of different proofs using different ideas, it goes back to 1850s, 1860s. No, actually, this one is 1890s. One thing I'll mention in a moment, it goes back to 1850s. And so it's a very, very old result, and very cute and very nice. So just to make sure that we are on the same page, because this one I will not prove, because it takes a little bit of work to do, and maybe if you're bored during the talk, you can try to do it by the end of the talk. It's not impossible, but I'll not do that one. But just to make sure we're on the same page and to have another example, which will be convenient at some points. And someone tell me what is the answer if we evaluate it over the cycle on n vertices. Yes, very good, and thank you. So you have a cycle on n vertices. How do you get a spanning tree? Well, you delete one edge. So a spanning tree needs to have exactly n minus 1 edges. So you need to delete one edge, and you have n choices. Okay? So This is just a kind of concrete example to keep in mind of what this function is. So historically, so another very interesting question about this function is, well, how hard is it computationally speaking? Right, so, and it turns out that this isn't actually that hard computationally speaking. There is a theorem that actually predates this Cayley's formula called matrix tree theorem, Kirchhoff's matrix tree theorem, goes to 1850s. And this is actually the theorem that maybe you've seen at some point in high school if you ever computed this or this resistance of a network of resistors type thing. So secretly, this spanning tree counting is kind of happening there in the background. And it tells you that if you want to compute this function for a specific graph, what you have to do is you look at the Laplacian matrix of your graph. So what that means is you put the degrees on the diagonal, and you take minus the adjacency matrix. Okay, so that's called Laplacian, that's a matrix. Determinant of that will be 0 because every row sums to 0, because we took minus on the adjacency and degrees there. But if you delete first row and first column, or any pair of columns corresponding row and columns, then the determinant of what is left, which is called the cofactor of this Laplacian, will be actually precisely what this function is. So this is, again, non-trivial result that probably, unless you've seen some tricks along this way, even by the end of the class, it's hard to do, but it's a theorem, and it has also very nice proofs, and it actually originated from physics. Or, well, in very different language and very different setting, but it's still attributed to Kirchhoff. Very cool. So now, because it's a determinant of a matrix, you can compute it quickly, and so this tells you that this function is not so sort of difficult computationally, and then you would maybe expect that it should be kind of very well understood, because it tends to be that parameters which are easy to compute tend to be easier to understand. But yet, there is some very basic questions about this that we have absolutely no idea about. And I want to talk about one specific one, and this is how large can the range of this function actually be? So how many different values can you actually hit when you evaluate this function over, say, all n-vertex graphs? Right, so we started and I told you that this is the maximum. Like, you can't hit more than that many values, and like, so specifically this is also upper bound on the number of things you can hit. But how many things do you actually hit up to that point? So it's a kind of arguably, I think, one of the most natural questions to ask when you have a function. How many values are, I mean, ideally we would like to know which values it hits, right? But that seems, I think, a bit too hard, and given that we can't even understand how many things you hit, I think that's definitely one of the most natural first things to ask. So this was asked in 1960s, so I can write it here. Sedláček, and it's late 1960s. Question is, how large is the size of tau g and over family graphs G, and he asked it for three very natural families. The first one is just all n-vertex graphs. Right, so you go over all n-vertex graphs, you input each individual into this function, you get a bunch of numbers. How many different numbers do you get? Okay. So you also asked it what happens if, or consider this question, what happens if you try to do this for planar graphs on n vertices? this is the same, except planar. So you input all n-vertex planar graphs, you see what you get. And the final one, so this I'm writing 60s, and it's actually 60s and early 70s, because he wrote about 5 or 6 papers around that time, and this was introduced in a variety of these papers and repeated in between them. So I'm sort of concatenating into a single question. What happens for regular graphs? So I want to tell you a little bit about all of these questions. I personally kind of find the first one the most natural and the nicest, but I think both B and C are interesting, and in particular also C, in some sense, for trying to understand something better about A, also makes a lot of sense. Very good. So is it clear? Is the question clear? Good. So let's look at some simple examples of this, just to make sure we're on the same page. And so let's try to compute tau of G. How did I denote it there? 3. Right, so here I'm asking really for a set, and I'm asking for all free vertex graphs. Right, so now if your free vertex graph is not connected, G, tau of G is just 0. Right, if it is connected but it is a tree, then the answer is 1. And the only free vertex graph which is not a tree and it's connected is a triangle. And how many spanning trees does this have? Well, 3, it's actually one of the C3 case there. Right, so you get that this spanning tree spectrum is 0, 1, 3. And the answer is we get at least 3 different values for 3. And then you can do the same example for 4 vertex graphs, and you can still compute it, and people computed this with computers also for a while. And but the question is really kind of how fast this grows. Very good. So also let me mention one thing that will be convenient at some point later, and this is that this is always an increasing function in a sense. So t, or set function if you want. So the spanning tree spectrum of n-1 vertex graphs is always contained in the spanning tree spectrum of n vertex graphs. And this is easy because for any graph that you have on n-1 vertices, if you just add a single pendant edge, that will keep the same tau, right? That if you want a spanning tree, you need to use that edge, and the rest is just what happened on the n-1. So whatever you can hit with n-1, you can hit with n. So these sets just get bigger and bigger, and are subsets, are nested subsets of each other. Very good. So let me now tell you something that is known about this function, and specifically the question of how big about this question. And I'll start with A, and then I'll comment something about B and C. So in one of these papers, from 66, so he proved that this thing grows, which is more of an observation, but so it grows at least linearly. It's not a very hard thing. Then in a subsequent paper from 69, we proved that to at least quadratic. And then he switched and actually did something about the other problems. I'll mention that. But it took some time to actually get some stronger results. So there was, in an Oberwolfach workshop, there is an abstract claiming that, so this was mid-70s, that they can do e to the root log n, which is roughly what, but this was first actually published in a paper by different authors, or at least I cannot find the old paper. So Azaria from 2014, who proved that it's at least 2 to the omega of root n over log. So this bound was claimed already in the 70s. It's like book of Oberhofer abstracts, but there is no paper. And also, really, this result is stronger. I'll get back to that point a bit later. It's talking about an inverse problem, but this is what it means in this original thing. Very good. And then there was another nice improvement. So this was by Stone, 22. And he got 2 to the n to the 2. So I don't know if there is some logs there. Maybe there should be some logs there, maybe. But let me put, just in case it's true, even if it's n to the 2. So this again is a result about the inverse problem, and this is what it means in the origin. So I'll explain what I mean by the inverse problem later, but I wanted to mention this. And also a little bit of number theory starts to come into both of these proofs, and somehow the basic starting idea that both these results kind of come from is that you can try to use these cycles and kind of chain cycles along edges, and then vary the length of the cycles as you go along, and then kind of try to exploit some, like, so what you can get is numbers which are products of a lot of small numbers. And then the question is how many such numbers you actually have, and this is something that number theory people understand very well. So this one is this is more or less a sketch of this, and this is a little bit more clever. Very good. Well, in the inverse problem, they're doing something more clever. But then just last year, well, now it's actually 2024, so there was an amazing paper by Chang, Kontorovich, Park, and they proved an exponential over bound here. So and really kind of the amazing
1.1, yeah?
what?
1.1?
Yes, roughly a bit better than 1.1.
We can see that point.
And really kind of the nice feature of this result is that it connected the problem, and it's using heavily some analytic number theory, specifically results of Bourgain and Kontorovich on Zaremba's conjecture about continued fractions. So it's a sort of very surprising connection, and that it actually translates so nicely. So technically, like, they also prove some version of the inverse result, and for this one you can get away without using heavy number theory, but still there is a little bit that goes in. So what I want to mention today, well, first of a few results that I want to mention today. So this is all, I wrote it there, but I didn't say it yet, joint work with Noga Alon and Bolinar. So what we prove is something slightly better, so 1.49 to the n. But really kind of the main point is that this is purely combinatorial, very simple, maybe like 1.5 2-page argument that I hope to show you. So I'll show you 1.41 to the n, just to kind of keep it even simpler for the talk, but with slight extra twist you can get a bit more. So somehow, like, not to jump from combinatorics to another area, but stick with combinatorics. Right, so also I should say that all of these results, they only use planar graphs. So actually all of the bounds written here also apply for the B version of the problem. And for planar graphs, this exponential behavior is the best you can hope for. So using these degeneracy properties of planar graphs, you can actually prove that it will not be higher than roughly 5 point something to the n. So for the planar graphs, this is the correct order of growth. But for the general graphs, as I said, the maximum is n to the n minus 2. And actually, it is possible and conjectured by Kontorovich and Bach, and I sort of believe that conjecture, that the answer here should actually be n to some constant n at least. So, and that remains open, and I think a very, very nice open program. Very good. So let me mention something about, so these all apply for planar graphs, but for regular graphs, much less was known. So in particular, none of these constructions really, unless you are, well, with some new ideas we have, you can tweak previous constructions and also get regular graphs. That's sort of the point. But by default, they don't. So what was known in the regular graph case, so that means the problem C there, Sedláček showed in 1969 that, well, it grows at least linearly for the free regular case. And then in a subsequent paper from 71, he extends this for any odd k. So note that there is a certain parity requirement of n and k for a k regular graph on n vertices to exist. And, so this is where that is sort of coming from. Technically, that is that nk should be even. Yes. So actually, maybe I wrote something slightly wrong here, but whatever needs to be for such graphs to exist. So yeah, if n is odd, then this cannot work. So maybe for even k is the correct thing to put here. No, we had odd there. What am I doing? Ah, yes, sorry, yes. I wrote it correctly.
So given the result for degree 3, it's not entirely obvious that for degree 5 it's...
Yeah, so this is a sort of thing that this problem definitely has a feature, that it's not really increasing in that way. So unless you have some sort of operation in which you can add the degree. So the problem is that kind of when you add some stuff to the graph, you lose control of what's happening with the tau. Right? So you have a lot of values that you get over the free regular things, but now depending how you add on top of it, some, let's say a Hamilton cycle or something that would maybe be natural, you might actually, like, it's not so easy to control. So somehow through this matrix tree theorem thing, you can think about it as a determinant. You're adding some sort of numbers on in the matrix, and you're trying to understand how that changes the term. So also partially some motivation, and I think the kind of that is very interesting here is that you can view this as like having some nice connections to random matrix theory, because like a very natural guess of what you might want to do is to take a random graph, and then you're asking for kind of how many different values do you expect a random, like over the random graphs of this to take. And in particular, it's like if you can prove good bounds on the so-called anti-concentration of the determinant of this random matrix, and this has been studied by a lot of people, and there is a lot of nice results, then you would get this as a consequence immediately. Because if you don't hit any value too many times with your random choice, then you need to hit a lot of values. So if you prove more than exponential anti-concentration, you get an improvement here. But the problem is that there equally there is the exponential anti-concentration, so is not, I think for this Laplacian version it's not even that is known, but for that might be doable with the existing ideas. But generally it's not known anything better than exponential, I think, in essentially any setting. So the more natural setting there is to just take the 0, 1 matrix or the minus 1, 1, and this is studied more often, but the Laplacian has also been looked at. And also, technically, Laplacian always hits 0 unless you take the cofactor. So it's another thing that makes it a less natural question to look at, maybe from the random matrix theory point of view. Very good. So I think I need to put n even here if I'm doing my handshake lemma correctly, but I probably did something strange. So, but it's required if I'm not mistaken. But definitely, first paper did the free regular case and this extended, so I don't know why only one of the parities, but yeah, okay. And specifically the one where this exists. Very good. Right, so these were essentially the only results that existed for the, I can keep it here, only results that were known in the regular case, and we managed to prove that in the regular case you still get exponentially many different things. And sort of the point here is somehow that the construction, like the argument we have and ideas are rather flexible, so they are much easier to tweak things than they were if you are kind of relying on the connections to number theory and so on. So here is theorem 2. Spanning spectrum of regular graphs is at least 2 to the constant n if nk is even. Very good. So that's the results that I wanted to mention. So for the rest of the talk, I would like to tell you how this is proved and essentially give you a full proof of, as I said, I will maybe sketch a little bit about the regular case, but I'd like to show you a proof of that with 1.41 so that I make my life a little bit easier. But it's really not much more complicated to get the better thing. It also suggests you can do even a bit better if you want to do the same type of thing a bit more complicated. Very good. So let me show you how we do this. So the basic idea is that instead of going and counting and kind of trying to keep control of the spanning tree spectrum of our graph, so we are going to build some family of graphs, right? So, and we want to have some sort of flexibility to tweak them so that we can get many different values of this. So instead of just focusing on what's happening with the count of the trees, we are going to actually introduce a certain two-dimensional vector that we are going to keep track of. The basic idea behind this is that if you keep track of more information, it's easier to reconstruct what happens after you do the operation. Right? So here, as I said already before, like if you change your graph, it's hard to keep track of what happens. So we need to pick our changes very carefully. And also these changes, you will not be able to keep track of what's going on when you do them if the only thing you remember is the number of spanning trees in your graph. So I want one extra parameter, one extra variable that I'm going to kind of be keeping track of through the process. So let me write what this is, and then it will make more sense. So if we have a graph G and an edge, we call G E a state. So really at any point I want to have a graph with a marked edge inside of it. And what I want to keep track of is the following function of the state. So if you have a graph and an edge, I want to know how many spanning trees there are in the graph G that use this edge E, and how many spanning trees there are in this graph G which don't use edge E. So I wrote it here in this form where we are contracting along the edge E, but it will never really matter. It's just a convenient notation. What you should think of this is number of spanning trees of G which use E. And this one is the ones that don't use E. So this one is obvious from this, I mean just G with the edge removed. That's precisely the number of spanning trees that don't use it. And here there is this famous formula that like the number of spanning trees is the sum of if you contract along an edge plus if you delete the edge. So this tells you, and also if you just think a little bit of what contraction does, you'll see that this is actually what happens there. But really for us, we're just keeping track of these two things, and this is my notation for that. Okay, because we'll never need this contraction operation in that way. Make sense? So now somehow instead of just keeping track of tau of G, I want to keep track when I'm going to be doing my operations of these two variables along the way. So when I make the change, I need to pick a new edge, and I need to create a new graph, and I will keep doing that.
Excuse me, when you do contraction, you keep multiple edges.
Yes, so this is how this usually works, but this, again, for me, it's just a matter of like counting how many spanning trees of my graph could use this edge. But yes, in terms of the contraction thing, and the multiple edges thing will show up in a moment. Let me get there in a few minutes. And I'll call this the tree counting vector, so just to have a name for it, because it will be showing up. Corresponding to the state G and E. Okay, so let me move to the other side. And before showing you kind of how exactly the construction works, we'll get to that in a moment. What I want to show you is that actually, if we manage to get a lot of different two-dimensional vectors of that type, then we win, and we sort of, like if we get exponentially many of those, then we actually also get exponentially many values for the tree, for the spanning tree function. So that we lose nothing by just by going and working with these sort of two-dimensional things. And we get a bit extra power in the sense that we have more memory when we are doing our operations. Very good. So, so I guess this I want to say that TU is feasible. It's actually n-feasible. It's a bad choice of letters. If there exists an n-vertex graph G, and E an edge of G, such that f of GE is right. So feasible means I can hit that vector with an n-vertex graph. Okay. So now here's a lemma, which is cute, simple, and it really tells you this that I kind of tried to summarize a second ago. That there is, like you can, it's enough to show that you get many n-feasible vectors instead of just showing that you need to get many spanning tree counts. So if there exists capital N distinct n-feasible vectors, then actually size of all n-vertex graphs is at least root. Right, and when we're talking about exponential functions, then taking a root just changes the constant in the exponent. So if that is like if we get exponentially many distinct n-feasible vectors, then we get exponentially many spanning tree counts. And of course, like if you add here planar feasible or regular feasible, you get the same story. Very good. So proof is very simple. It's sort of a pigeonhole basic Ramsey argument. So let me label our feasible vectors. Notation. Right, so let me give names to this. And let's go one coordinate at a time. So if we get root n distinct second coordinates, then we are done, right? Because remember, what is the second coordinate of this vector? Just a spanning tree count of some n-vertex graph, right? This G minus E is still an n-vertex graph. So if you get root n many different values in the second coordinates, you're done. You got your root n different. So if at least root n distinct values among u1 up to un, then we are done.
In which
Yes.
class are we?
So you can do it in whichever you want, but I'm only talking, let's say, about the all n-vertex graphs.
This statement is not
So I mean, like,
regular, right?
so like, if you want it for regular, you can insert. Well, okay, yes, true. It will break the regularity.
Okay.
Yes, yes, you are correct. Yes. So regularity we do differently. For planar, it is true. Yes. Thank you. That is a good point. For regularity, it's a slightly different tweak. So I'll get back to that later. But yeah. Right? So, and if you don't have root n distinct values, that means that one of them appears root n times. Right? You have one value that appears root n times. And since the vectors are distinct, that means that on those root n vectors, you get the first coordinate being distinct. If less than root n, so let's call these u1 to u root n. Right, so I mean, right, and now this implies that, well, T1 and T root n are distinct. Now there are two different ways of finishing, both are very simple. So I like it better to just add up these numbers. So just say that this also means that T1 plus U1, T root n plus U root n are distinct. Right, if you have equal numbers and distinct numbers, and you add the equal number to all of them, they stay distinct. And these are simply the spanning tree counts of n-vertex graphs as well, right? So this was this business about if you sum these two things, you get all the spanning trees of G. So we're done. So these are again also spanning tree counts. Also done. It proves the lemma.
What's the second way of finishing?
So just using kind of the fact that this, you can tweak a little bit to kind of make it you can also make that into an n-vertex graph. So like that's also a graph on actually less vertices. It might be a multi-graph, so you need to be a little bit careful what you do there. But like if it's not a multi, you just add the pendant edge and you make it an n-vertex.
I see.
So you can just stick at the T1 thing, but you need to, right now I don't, there was a way to get around the multi-edges there as well. But I think this is kind of too meaningless.
That's very good.
Yeah. So very good. So now we reduced our problem of kind of finding many different values of tau to finding many different values of this tree counting vector. So I think now I can actually show you construction. So it's actually good. So I'll sort of show you 2/3 of the construction because the final third is to get a bit better numbers, and the 2 parts are enough. So I want to have 2 operations on a graph that I can perform, and after I perform them, I want to understand. I want to maintain, kind of understand what happened to these tree counting vectors. Right, so our input is, so let's call this operation A. So let's call this subdivision. So our input is a graph G and an edge E. Right, and we know of this, the tree counting vector. So this is, let's say that f of G E is du. And the operation that I want to do is just put a vertex in the middle. Right, so it's a simple, sensible operation. Keeps planarity if you want to do planar. So I need to also tell you where I put the marked edge, U1. But these two are the same, and these are sort of the only ones where we can sort of hope to do anything, so we'll just put it there. Let me call this G prime and E prime. So now I'm interested in what is the tree counting vector for this graph. In other words, how does this 2-dimensional vector evolve over when we do this operation? And again, this is not hard to do. Like the first coordinate is the number of spanning trees which use this E prime in this new graph, right? So if I use E prime, I have one decision to make, 2 choices. Do I use the other edge or not? If I do not use it, then I have exactly the same thing as if I didn't use E in G, right? So if I delete this is a pendant edge, I have to use it, and everything else is just a copy of G minus E. Right? And that was precisely U. So, right? So we get U if we don't use that edge. If we do use this edge, well, this is the same as if we just had an edge, right? So we get the other coordinate of that, so we get a T. Right? So the second coordinate, and that's it. We just counted the spanning trees of this. How about the second coordinate? So this means if we delete this E prime, well, we just actually talked about this and said that this is equal to count of G minus E, which is just U. Right, so this is how the 2-dimensional vector evolves, and it's convenient to write this as a matrix product. Right, so it's a matrix 1, 1, 0, 1 times Tu, and let's call this matrix A for operation A. Okay, so that's one of the operations. Of course, on its own, it's rather silly, because what is it doing? You start from an edge, or from whatever you want, and you're just subdividing the edge, so you get a long cycle, or you get a long path, or something. Nothing really happens. So we need at least 2 operations, so let me tell you what the other one is. I'll call this operation B. And I like to call this doubling. So what does that mean? Again, as our input is, we have a graph G, a marked edge E. We have this tree counting vector, and we're want to do an operation. So this one, what we'll do is it will just double this edge E that we have. So we again are going into multigraphs. And I should have said at the beginning that all my definitions are for simple graphs. I don't allow you to cheat with multigraphs, because with that you can cheat as much as, like, you can get anything you want, essentially. Just put as many copies on the edge as you want. There are interesting questions about multigraphs as well, but they are slightly differently formulated. They care about the number of edges you use rather than the vertices. Let me not go into that. I'll say one word later on what people know how to do about that. So this is sort of a problematic operation. But so let me tell you immediately how we'll fix it, and then we can do the same computation. So if you do this operation, you are now in a multigraph. But if I immediately follow it by that operation, then I'm going to split this new edge into two, and now I'm no longer a multigraph. Right? So long as we insist that we only do one operation B at a time, we stay within actual simple graphs. Okay? So we'll get back to that point when we actually compute what this is doing. But so far, let's just figure out how the vector evolves if I do this operation. Okay, so and it's the same computation as before, right? So this is du.
But the definition of the coordinates of the vector were for simple graphs.
What, sorry?
T and U was for simple graphs, not for multigraphs.
So T and U, so this thing, I mean, it works exactly the same if you have if you plug in a multigraph here. So what I meant was about the tau, actually. So this one, well, okay, the result about the spectrum size is only allowed to plug in simple graphs when you do the spectrum. But you are correct, yes. So here the definition makes sense, and I wanted to, I mean, just, again, I can also just do immediately the combination of operations, but this works a little bit cleaner if I do it that way. So this is more auxiliary, so only very temporarily will we ever be multigraph. Very good. So what is this? So again, we want to count spanning trees that use this edge E prime, and again, they are the same, so whichever one you mark, you mark. So if you use it, you're not allowed to use the other one, and then you are just in G, which is using E. So this time you just get T here. If you don't use it, you have a choice whether you use the other one or not. If you use it, you're again in just this one using E. If you don't use it, you're in this one not using it. So here we get the sum. And then this is different matrix times T. Right, so now we have two different operations that we can do. And now the game is simply to analyze how many different things do we get. Right, so
What do you start with?
What?
What do you start with?
So we'll start with an edge, but technically you can start with whatever you like. I mean, yes, that is true. I mean, if you start with something a bit bigger, you'll get worse numbers, but right, so now what I essentially showed you a proof of is a lemma or theorem that for any A1, AK bigger or equal than 1, A to the A1 times B times A to the A2 times B times A to the AK times B times 1, 0 is A1 plus blah, blah, blah plus AK plus 2 feasible. Right, so I'm starting from an edge, which this is the tree counting vector of an edge. It's just one tree if you use it, 0 if you don't use it. And then I'm alternating between these operations, except I remember that I'm only allowed to use B once consecutively, so that we stick with simple graphs. Right, so I could start also with a to the ak plus 1 if I wish. It doesn't change much. And why is it this feasible? So if you think about it, this operation does not cost you a new vertex, right? Whereas this one does. It creates a new vertex. So whenever you use a B operation, it's free. Whenever you use an A operation, you need to add a vertex, and we start from 2 vertices. So you get A1 plus A2 plus AK plus 2 as the total number of vertices in a graph that kind of will have this as its tree counting. Okay, very good. So now the question is, how many different things, how many different vectors do you get by doing this? And so one question is, well, how many different choices of this sum do you have? Right, so we want we are interested in n feasible vectors, so n should be and these need to be at least 1. Again, this is the point of not repeating operation B twice. So has 2 to the n minus 2 solutions. Note that we get to pick k as well. So how many alterations we do is the same. And this is just like you pick your favorite subset of n minus. So you move the 2 there, you pick your favorite subset, and then you use it as kind of this balls and bins, like the boundaries of where your sums will be. So that's a bijection proof. You can also actually just use balls and bins and count. But the point is there is exponentially many solutions to this. So we have exponentially many choices. But this is not yet enough. So you sure.
Okay, so you want to use
I want
A
to
after each B, but you want to use it in a specific place. Otherwise, you want to put the new vertex at this one of these edges.
True.
Otherwise, you are.
Yes. But we have a marked edge, right? So like the things that we are keeping here in both results.
Always put the vertex on the
yes.
marker.
So this one, it required that like you don't get to choose where you put it because you don't know what's happening anywhere else.
Yes.
So this is kind of this like information that we're storing in the 2-dimensional vector.
Yes.
Like you only really know what's going on around your edge. If you try to do this somewhere else, you will lose control.
Yes.
So this specifically kind of is designed so that you can subdivide also the.
Okay, and then again, could you repeat this argument? Why do we have 2 to the n minus 2 solutions?
K is also a variable, right? So you get to choose how many times you do, well, how many B operations you do in total, let's say.
Yes.
And when you get to choose that, then you can do 1, you can do 0, you can do up to I guess n minus 2 or something like that. Yes. Makes sense. And so there is a neat bijection proof of this that you just take a subset of n minus 2 elements, and for every subset you'll get a unique solution. Namely, kind of the subsets are the boundaries between the value, like the difference between the entries in your subset are going to be this. Okay. You can also do the more basic, like this balls and bins argument. If you fix k and you sum up some binomials, you get the same. Okay. So far we are doing sort of well with one issue, right? So we hit a lot of different 2-dimensional vectors, and well, we have a lot of choices for A1 up to AK, right? But why is this not immediately?
So 1.41 stands for square root of 2, huh?
Yes. So yes.
Okay.
Very good. That's where that is coming from. Yes, I want to take a square root of this using the other lemma. But before that, I want a statement that says that actually any choice of A1 up to AK here that does this will give you a different vector. Right? Because if we have this many choices of A1 up to AK, no one guarantees us that somehow they don't conspire and give us all the same values somehow. So this doesn't happen, and it's a cute argument. So specifically, if you think about it for a moment, if you look at these two matrices, I did not name this one B. If you multiply by A, you will always get the bigger first coordinate. So long as our vectors are all positive, no negative, actually ignore this 0, but this is the one that matters. Whereas the B operation will always give you a bigger second coordinate. So if I give you a vector that came out of this process, I can easily decode back what these numbers are. I just look whether my first number is bigger or the second one. That meant I use A. I multiply by A inverse, and I keep doing that. And that tells you that this actually always gives unique. So I'll not write it out, but I think it's each. And now we're done, right? Because we have the other lemma that, so this tells us you get this many different feasible vectors. The other lemma says you get root of that many different tree counts. So you get 1.41. Very good. So that's the whole proof. And I'm not even cheating or lying anywhere, I think. So also,
okay, but the only degree is not.
Yeah, so for the regular case, this will not work. So I can comment on how you fix the regular case. So for the regular case, what we'll do is we are going to insist somehow. So you also kind of can track how these graphs look like, actually, if you think a little bit about this. So they are just chains of cycles where kind of, they look something like that, right? Where these are like how many times you did the subdivision operation before doubling and so on. So you can count how many vertices of degree 2 and 3 you get here. And if you insist on how many operations, like if you fix the k here to be something like n over 2 or whatever, this will still give you exponentially many solutions. But now I'm doing kind of exactly the same number of subdividings, which will fix you the number of degree 3 vertices.
Wait, when you draw these cycles, so when you start with this cycle, this should be a direct edge actually. Because this is the moment you introduce a multiple, and then you subdivide the new multiple one, yeah?
True.
Yeah.
True.
Yeah, right.
Some point we wanted this picture, but yeah, you're right, I think.
Yeah.
You're right, yeah. So essentially you can control, when doing this, you can control the number of degree 3 and degree 2 vertices. So they're all degree 2 or 3. And we still get exponentially many choices for like, even with a fixed count of degree 3 vertices. And then you simply kind of insert some gadget to each degree 2 vertex that looks something like the picture there, but maybe yes. Looks something like a pendant. Right, so this will have degree 3 everywhere, except kind of there, like it sends one pendant edge out. And also it will just multiply the total spanning tree count by some fixed number, which is sort of the number of spanning trees of this thing. And since we have the same number of degree 2 vertices, you always use the same number of these things, so you always multiply by the same number. So you still get exponentially many different things. And then for higher degrees, you need to do like slightly more clever version of how this works. And with some parity, you need to be a bit more careful, but this gives you the free regular case. Very good. I'm slowly, but let me mention some open problems. So one I already mentioned, and I think it's kind of the...
Excuse me, so to do something in order to apply the square root like this lemma 2.
So sorry. What,
when you are doing the regular graphs, right? How do you go around the lemma 2?
So this will still spit you out, right? A family of so because you don't like there that but like one of the proofs. So I can do. So I think I can do this first, and then so get a list of. See. Good question. So like in the first case, you're definitely fine because you just get the family of these things. But in the second case, you're deleting the single edge.
In the case where you remove edge, you can add two gadgets and get a little bit larger and put the same number.
True, but you somehow then you will kind of run into trouble when you have the So I don't right now remember how exactly we were doing that. Yes, that is a good point. Yes. Okay, let me think offline and I'll tell you what happens. But yeah, I don't remember right now.
Maybe you use a couple of gadgets with slightly different size.
That's plausible, but that is not what we're doing. So I'm trying to remember what we're doing. But yeah, I think that's not what we're doing.
To compensate for the number of gadgets.
Yes.
So I have another.
Yeah.
How do you improve from root 2 to 1.5?
Yeah, so you add an operation C, which is kind of and which is sort of similar, but like it saves you a vertex. And I think it's like so. Essentially, when you do these two, you're adding a triangle there, and like so. Technically, you choose on the triangles. I think you will get actually the pictures that I was drawing before, because the operation C will allow you to kind of subdivide the old edge and not the two new ones. So somehow, right? You have an edge here, and when you do these two operations, you will always by these operations mark one of these things, but you can also mark this one. And if you do that, you get kind of a third matrix that can go into the picture, and it essentially it's a product of A and B of some form, but it kind of it only adds one vertex and kind of gives you two matrices A or something like that. So you can save a little bit by doing this type of trigger. And I'm sure that if you keep adding more operations, you can have more things here. And I need to think about. I don't remember yet. This was.
It's open problems.
What?
Tell us the open problems.
Ah, yes. Sorry, I got distracted. So one is the conjecture, and it was asked explicitly in this paper of Kontorovich and Pak. So the size of tau of Gn should be at least n to the omega n. So I think this is kind of very, very nice, and still sort of the problem here is that this naturally builds very sparse graphs and even planar ones, and somehow with those you are limited to exponential. So you need a more complicated operation, but when you have a more complicated operation, the analysis becomes harder. So there is a sort of trade-off between the two. Right, so the second one is a so-called inverse conjecture. So the inverse problem here is, suppose I give you a number t, how big a graph do you need to take? So, or like how small a graph can you actually take so that its spanning tree count is equal to t? So conjecture, you write it here.
Existence trivial?
Yes, because of the cycles, except for 2. But very good question, yes. So conjecture for any t positive t greater than 2 integer there exists a graph on big O of log t vertices which g as tau of g equal to t. So this would imply the exponential growth there. And actually, it's even feasible that here it's log t over log t. So that would imply that conjecture. But here, even the kind of exponential analog is still open. And the best result here is, well, the best universal result is back to one of the papers I mentioned before by Stone, 22, which gives you log to the 3/2 here. So that was there e to the n to the 2/3, if you remember. So if you invert some functions, you get log to the 3/2 here. And also, Chan, Kontorovich, and Pak proved that this is true for almost all integers. So for a set of positive upper density, let's say. So for most integers, you will be able to do that. So the question is, like, can you really do it for all of them? And this is still using the number theory stuff. So this we don't know how to get rid of, even if you just want to hit any of these things. Right. So I think kind of both these questions are very nice. So let me stop there. Thank you for your attention.